Hi, and welcome back to my series of videos for Physical Chemistry 1. Today, I want to look at what happens after the reaction's at equilibrium. It turns out that when a reaction reaches equilibrium, it may not necessarily stay there. For example, suppose we have this reaction, in which acetic acid dissociates to form hydrogen ions and acetate ions. It's a reversible reaction, and the equilibrium constant has a value of 1.8 times 10 to the minus 5. But now, suppose we add some more H plus ions to the solution. What will happen? If we do that, we're adding a product, and that means this ratio will increase, and it'll become larger than K. However, reversible reactions always try to be at equilibrium. In this case, that means the direction of the reaction will change so that the amount of product will decrease. In other words, because we added some additional product, the reaction will shift to the left to try to get rid of some of what we added. A similar idea also happens if we add reactant. So, if this reaction was at equilibrium and we add some acetic acid, there will be too much reactant now, so the reaction will shift to the right to try to get rid of it. We can get something similar to happen if we take away a compound instead of adding one. For example, suppose the reaction's at equilibrium and we somehow take away hydrogen ions. In that case, now there's not enough product, so the reaction will try to replace what we took away. So the reaction will shift to the right. In the same way, if we take away some of the reactants, the reaction will shift to the left. This is a pretty simple idea, but as we'll see in later videos, this simple idea, that a reaction will change direction if we add or take away a compound in the reaction, is a crucial reason why living things are able to maintain homeostasis, where the balance of molecules and ions in the cells and body fluids are kept within a range that helps to keep the organism alive. This behavior of chemical reactions was discovered in 1888 by the French chemist Henri Le Chatelier, so it's called Le Chatelier's principle. It states that when an equilibrium is disturbed by adding or removing one of the compounds, the direction of the reaction shifts so that eventually the equilibrium is restored. It's one of the most important ideas in chemistry and biology, so let's look at another example. Suppose we have this reaction. Calcium ions and sulfate ions react to form solid calcium sulfate, and this reaction is at equilibrium. But now we remove the solid calcium sulfate. For example, we could do that by pouring the solution through a piece of filter paper so that the ions would go through the paper, but the calcium sulfate would be filtered out. When we do that, that means we've removed calcium sulfate from the reaction. So Le Chatelier's principle tells us the reaction will shift to the right in order to get back to equilibrium. There's one more interesting way that Le Chatelier's principle can affect the direction of a chemical reaction. Suppose we have the following reaction, which is an exothermic reaction. Just like any other reversible reaction, Le Chatelier's principle tells us that the reaction will change direction if we add or remove one of the chemicals. But remember, I mentioned a moment ago that this is an exothermic reaction. That means it releases heat, so we can think of heat as being a product of this reaction. We can show that by writing the symbol for enthalpy, delta H, on the product side of the reaction. But think about what that means. Le Chatelier's principle tells us that if we add one of the products, the reaction will shift to the left. That includes the heat. So, if we heat up the container in which this reaction happens, we'll shift the reaction to the left. On the other hand, if we cool down the container, it's like we're taking away heat. So that means we're taking away a product, so the reaction would shift to the right. Let's try another example. Suppose we have this reaction. This one is an endothermic reaction, which means the reaction absorbs heat. So heat goes into the reaction, not out of it, and the delta H then belongs on the reactant side. What will happen if we heat this container? In that case, we're adding a reactant, so the reaction will shift to the right. As you can see, Le Chatelier's principle really only applies to reversible reactions, since an irreversible reaction can't change directions. Let's do a calculation for a reversible reaction at equilibrium. For example, suppose we have a 0.100 molar solution of iodic acid, HiO3. What's its pH? This sounds pretty simple. At first you might think we could just plug 0.100 molar into the pH formula. But that's not right. You might remember that when strong acids or bases dissociate in water, it's an irreversible reaction. That means that if a strong acid has a concentration of 0.100 molar, that'll also be the concentration of H+ ions in the solution. But for a weak acid, that's not true. The reverse reaction happens at the same time as the forward reaction, so all the acid molecules are never completely dissociated into H+ ions. So, how can we find the pH? The way to find out the amount of product like H+ in a reversible reaction is to use a Rice table. If you don't remember how Rice tables work, it would be a good idea to go back and look at those two videos now, because we're going to use them a lot in the rest of this video and in class. So, here's our Rice table. From the last video, you should know that the acid dissociation reaction for iodic acid is this. The first thing we need is the initial concentrations. The problem tells us that we have 0.100 molar iodic acid. The iodic acid will dissociate, but before it does, the H+ and iodate ion concentrations are both 0. That'll usually be the case for weak acids and bases. Whenever a problem tells you that a weak acid or base has a certain concentration, that's its initial concentration before the dissociation has happened. Right now, we don't know how much the concentrations will change, but we do know that the concentration of each product will go up by the same amount, because the reaction tells us that they're in a 1-to-1 ratio. For now, let's just say that they go up by an amount x, and we'll figure out what that is later. Since the reactant is also in a 1-to-1 ratio with the products, its concentration will change by the same amount, but it'll decrease, so the change for it is minus x. That means our final concentrations are 0.100 minus x for the iodic acid, and x for the H+ and iodate ions. In order to get the pH, we need to know the H+ concentration, which is x. How do we get that? We use the equilibrium expression. For this reaction, we have Ka is equal to the products over the reactants, which is this expression. To solve the equation, we need to know what the value of Ka is, which we get from Appendix D of your textbook. If you look there, you'll find out that it's 0.17. Now we can use this equation to find x. The numerator is the same as x squared. Next, I'll get rid of the denominator by multiplying the right side by 0.100 minus x. Now I'll move everything to the left side of the equation, which gives us x squared plus 0.17x minus 0.017 equals 0. This is a quadratic equation, so we'll use the quadratic formula to find the solution. Please feel free to use a programmable calculator to do this the fast way. When you do, you find out that x has two possible values, 0.0706 or negative 0.241. As usual, one of these two answers must be impossible, and in this case it's the negative number. We can't have a negative concentration, so that means the H+ concentration is 0.0706 molar. When we use that in the formula for pH, we find out that the pH is 1.15. But there's one problem with solving problems like this one using the equations we've used up to now. You might recall that we often model gases as ideal gases and solutions as ideal solutions. However, real gases and solutions behave somewhat differently, and that means that the equations we've used so far will give us inaccurate results. Back in video 35, we found out that we could describe the extent to which a gas deviates from ideality using the activity, which is given by this equation. Back then, we saw that for an ideal gas, this would be just equal to the mole fraction. But remember, back when we were discussing the reaction quotient back in video 39, we saw this equation. The large fraction is the reaction quotient, Q, and if you compare this to the expression we have for activity, you can see that each of the 4 terms in the large fraction is just equal to one of the activities. That means we can rewrite the definition of the reaction quotient this way. This is really a more accurate way of writing the reaction quotient. Using activities instead of pressures or concentrations can give us significantly different and more realistic results. However, it's not very obvious how we could relate this to the reaction quotient we're used to, which is written using concentrations or pressures. How can we connect this equation to the more familiar versions of Q or K? For example, suppose we're studying a system at equilibrium. In that case, we could write the equilibrium constant this way. You might recall that there's also a quantity known as the activity coefficient, and for solutions, we can define it using this expression. If we rearrange that to solve for the activity, we get this. We can use that expression for the activity in our expression for K, which gives us this. We can make that a little simpler to understand if we place all the activity coefficients into their own separate fraction, which gives us this. This expression is known as the thermodynamic equilibrium constant, and it's a much more accurate way of thinking about the equilibrium of a reaction taking place in gas or aqueous phases. Well, that brings us to the end of our course. I hope you do well on your exams and that you learned some interesting things this semester. In Physical Chemistry 2, we'll look at a completely new topic, quantum mechanics, the study of the energy and motion of particles like electrons and how they interact with each other and with light. The ideas we'll explore are the basis for our whole understanding of chemistry and how atoms and molecules interact. It's a fun and interesting subject, so I hope you'll be able to take that course. In the meantime, good luck on your exams, and enjoy the end of your semester. I hope to see you in PChem 2.